Hey guys, welcome to lecture number 27. Well, this is a very important lecture. We will be talking about integration by substitution. You will see how this will be related to all the techniques that we have learned so far. And I would like to remind you that at this point, we have seen how to compute indefinite or even definite integrals, most of the hard way or the easy way. And the easy way was using the fundamental theorem of calculus. But now, in this lecture, we'll do something a little bit tricky. And, well, using some of them, when we want to compute an integral, by doing some kind of substitution, we need some kind of inspiration. Well, some of them are pretty obvious, but some of others are not that obvious. So we need to see what kind of substitution should we perform. Also, I would like to in today's lecture, I would like to show you many examples of the how to use U substitution for integrals, both indefinite and definite integrals. And I would like to tell you that this is an important lecture because it will be relevant for your gateway exam and especially for your final exam. All right, so let's get started. All right, so well, integration by substitution, this is what we will call today's lecture, and it will be a little bit of a longer lecture, but anyway, hopefully we're going to get through it. All right, let me dive in directly and tell you exactly what this is all about. So, let's see. Let me, if you want, for example, to differentiate, right? If you take the function sine of 2x, and if you want to take the derivative with respect to x, right? Well, it's quite clear by using the chain rule, right? Remember, let me remind you that usually sine of u of x, and I want you to pay attention here, right? Prime is what? Is cosine of u of x times this guy here, u prime of x, right? This is the chain rule. Applies for, well, in our case, u of x is nothing else than just 2x. And of course, this implies that u prime of x is 2, right? All right, great. So according to the chain rule, it's pretty clear at this point that the derivative of sine of 2x with respect to x is 2 cosine of 2x. Great. So that's the derivative. But if we want to perform the inverse operation, right? If we want to take the antiderivative of 2 cosine of 2x, so basically, if we integrate this function, we will get back the function sine of 2x. Well, plus c, if we're dealing with an indefinite integral. All right. Well, in general, if we like to, so if we have, if we denote f of u to be y, dy over dx is nothing else than just f prime of u times du over dx, right? And u is a function of x, right? It's like u of x. And I want you to pay attention to this because this is important here, because this is what will allow us to perform our u sub. But anyway, since we have this, well, if we want to go back, right, to take the to apply the inverse operation, basically, if we would like to integrate, then we will have that this indefinite integral here, right? F prime of u. And pay attention, times du over dx times dx equals f of u plus constant. So again, this is a very important formula. Right? It's pretty clear that this would happen. Right? We just go back with, we integrate the equality in red. And there we go. All right, so this is basically what we do. Well, I didn't quite say what is the U sub here, but we'll see that through some examples. And let me start with an easy example first. So example number 1, ouch. All right. So example number 1, let me write it here. Says the following. We need to find cosine of 2x dx. So let's think about that for a second. And pay attention, we would like to perform a U substitution that would make our life easier when we compute that integral. And what that substitution would be? That is the question. Exactly like Eric says, this would be pretty obvious that the substitution that we should perform here would be U equals 2x. Indeed, let's do that. So we perform U to be equals 2x, right? Okay, great. And now pay attention. If U is a function of x, let's say g of x, then du is g prime of x dx. So du will be 2 times dx, right? Or if you want, you can say that 1/2 du is dx. Okay, let's keep this relation in mind. Because when we'll perform the U sub, we will have to use this, right? So this guy here. Great. So now our integral will become what? Let's see. So the integral of cosine of 2x dx, well, as we know, 2x is u, so it will be the integral of cosine of u, right? But we also have to replace dx. And look here, dx, this guy dx here is right here. Because we changed a variable now. So everything we have a new variable. U is not x anymore. So this is what we call the U substitution. So we take what's with x and we transform everything in terms of u. And as you can see in the initial integral, we have the cosine of 2x times dx. So we would like to see everything that has x in it, we'd like to see u there instead of x. All right, so once we do this, so we will have that this integral will transform into the integral of cosine of u. And since dx is 1/2 du, as you can see here, this is dx, right? Then this is the integral we would like to compute. So basically this is 1/2 cosine of u du. We can take the constant 1/2 in front of it. So we will have that this is 1/2 the integral of cosine of u du, right? And now, well, we can compute this, the antiderivative of this. What is the antiderivative of cosine of u du is what? What is it? Pay attention, it's the antiderivative, not the derivative. Travis. That's why I'm asking questions. So the derivative, yes, it is that. But the antiderivative, what is the function whose derivative will give you cosine? It's sine. So this will be sine of u, 1/2 sine of u plus constant plus c. All right, great. But now, are we done? Not yet. What we need to do at this point, you see, the questions asks us to find the integral in terms to find the integral in terms of x. So the result should be something in terms of x, but it's not. It's in terms of u. So we go back to our initial substitution, right? Because we said that u equals 2x is right here. Look at it. And the final result will be 1/2 sine of 2x plus c. See, I want to stress this out. Don't forget to go back to x. This is important. Don't forget to do that. All right, so that was an example, first example. Now let's see another one, maybe a little bit more complicated. So this is example 2. So we would like to find this integral. Find the integral of x times the square root of x squared plus 3. Let's see. So do you, yeah, maybe, why not? Well, that could be an idea. So let's see, what if we try this? So let's try u to be x squared plus 3. So let's see if this fits, if this substitution is fits into the picture. So we will have du is what? Is dx squared plus 3, but dx squared plus 3 is, you know, is dx squared. Let me write it like this so that you see d, let's say 3, but dx squared will be 2x dx plus 0, which is 2x dx. Great. Wow, that's actually a very good one because I already have, look here, if you look at this guy here, x and dx, x dx, well, it's already here almost. So it's a, this is a good one. Great. All right. So let's see. By performing this, as we have already seen, we can write that 1/2 du will end up that 1/2 du is x dx. Always when you, let me give you a piece of advice. Always when you do this kind of substitutions, make sure you you separate the variables, what's with u, what's with x. So you try to write everything that has u in terms of x or the other way around, right? Because because this is what I would like to do since I'm changing the variable from x to u. All right, so we can write this as 1/2 du equals x dx. All right, beautiful. Well, since I can do this, I can, my integral, guess what? X dx will be 1/2 du, right? Do not, as you can see here. So this guy, x dx is 1/2 du, and the square root of x squared plus 3 is nothing else, just the square root of u. Wow, great. At this point, I can take the constant out, and this will be nothing else, and I can write the radical as u to the power 1/2. So this would be nothing else than just 1/2 times the integral of u to the power 1/2 du. All right, and now I know how to integrate this, right? I know usually how to integrate the power functions. So in this case, we'll have what? This will be 1/2 plus times 2/3 times u to the power 3/2 plus c. So this is how we're gonna compute the integral, right? Let me remind you this part here. Is this part here, if you want. But anyway, that constant doesn't, well, you can say it's 1/2 times that, but 1/2 times c, you can denote it by another constant, so it doesn't really matter. All right, but now do not forget to go back to x, and now we're going back. So finally, this will give us that, well, since I my initial substitution was this one here. When I go back to x, I'll have that this integral will be 1/3 times x squared plus 3 to the power 3/2 plus c, right? Okay, let's see. Any questions so far? Is everything clear? All right, that's great. Let's see another example now. I would like to do even a more complicated example. In fact, I'd like to do this together. So the following example, so example number 3. So here we would like to find the integral, the indefinite integral of the following: e to the power of 4x cubed plus 7 times 2x squared. So I'd like you to think of this for a bit. Give me 1 second. All right, let's see. So what kind of substitution would you perform here? You see, it's kind of ugly, that integral. It looks like it doesn't look appealing in any way. So it will be pretty. I would not advise you to compute it just directly like that. So maybe you would like to make your life easier a bit. Let's see. Abdul says, well, yeah, why not? Here we would perform the substitution u equals 4x cubed plus 7. Yes, why not? So let's see. That could be like an idea. So u equals 4x cubed plus 7. Make sure you perform a substitution. You have to do it you have to be wise with it, because you need to see the differential as well. So let's see, du equals d 4x cubed plus 7, and this would be d 4x cubed plus d of 7. And this guy will be 4 times dx cubed plus 0, which is 4 times, let's see, 3x squared dx. All right, and this would give us 12x squared dx. That's important. So du here, right, is this guy here. Right? All right, great. Let's do that. Let's see, do we have something? Look at this guy here. This part here, x squared times dx. You see, you can actually put even two there, but anyway, it doesn't matter the constant that much. It's already there. It's a part of du. That's actually a very good substitution. So it's you see, you have to be productive when you do the u sub, so that you can make your life way easier. So let's see again, just like we saw, and we can write this. Well, if you want to see this, well, I said that du is 12x squared dx, or you can say that 1/6 times du is nothing else than just 2x squared dx. All right, great. And now let's see, our integral will become the following. Wow, look how easy it looks now. So e to the power 4x cubed plus 7 will become e to the power u, and 2x squared dx will be 1/6 du. Well, that's great. We can take 1/6 outside of the integral. And now we know how to compute this guy here. This guy is what? Can you tell me what is the integral of e to the power u du is what? Is e to the power u, right? So it's the same. So it's 1/6 times e to the power u plus c. But we're not done. We have to go back now. And we're going back. We're going to replace u by 4x cubed plus 7. And then the final answer will be 1/6 times e to the power 4x cubed plus 7 plus constant c. So that's the final answer for this integral. Let's see, any other questions? Is it clear how to compute these integrals? Like I said, you have to, the moral of the story in this problem is that you have to just perform a certain substitution that will make your life way easier. You see at the beginning how ugly this integral looks like, and well, I wouldn't say very ugly, but very unpleasant, I could say the least. And look, once you perform that u sub, then your life is it's much easier. All right, let me go further a bit with another example. So example number 4. What about this one? So in this example, we would like to find the integral of secant squared of 3x minus 1 dx. So secant squared of 3x minus 1. Let's see. But first, let me remind you something. What is the integral of secant squared of a function of u, for example, du? Let me remind you that this guy, so the integral of the secant square is nothing else than just is tangent of u plus c. Remember that? The derivative of the tangent is secant square. So the integral of the secant square will be the tangent plus c. All right, great. Let's see. Having this in mind, what would you suggest to do? Yes, that could be an idea. U equals 3x minus 1, why not? So let's write it here. So u equals 3x minus 1. Oh, sorry, let me just change the color. And for here, this implies that du is what? Is d 3x minus 1, but anyway, this will be just 3 dx. Great. So in other words, this will imply that 1/3, so it will imply this. 1/3 times du equals dx. All right, great. So now let's compute this, go further. So our integral will become, you look how easy this becomes. So the integral of secant squared of 3x minus 1 will become the integral of secant squared of u times 1/3 du. All right, beautiful. And now we know from here, from here, we know that secant squared of u, so we're going to take 1/3 out. So it will be nothing else than just 1/3 times the integral of secant squared of u du. Well, we know what the integral of secant squared of u is. So this would be 1/3 times the tangent of u plus c. But we're not done. Keep in mind that we need to go back to the initial substitution. So we need to go back to the x variable. But we know who u is, so it's 3x minus 1. So the final result will be 1/3 times tangent of 3x minus 1 plus c. So that's this is how we solve this problem. As you have seen, the main ingredient is to know that the antiderivative of secant square of u is the tangent, right? And then you just perform the u sub, which is pretty obvious in this case, is 3x minus 1. And then that's pretty much it. All right, let's see, any questions regarding this example? Let's see. No questions, okay. It's everything clear so far? All right, great. Please don't be shy. I think it's at this point, what am I talking about? I'm talking to the 44 people, half of the class who actually cares about the class. So anyway, but in any case, feel free to address questions. Well, according to my investigations, those who do not care about the class, they don't even show up. So anyway, 44 of how many? 85. So half of people are showing up to class, unfortunately. And 12 of them, actually 10 of them, 85, yes, 10 of them do not care at all about this class. They don't take any exams, they don't do any homework, nothing. They don't show up to class. They don't even read my email. So just like I said in that email, I was not kidding. I was actually very serious. Yes, that's exactly what I said. It's money wasted. But anyway, who am I to judge? You know, everybody runs its own life the way they want to. So yeah, that's the same question I have too, but anyway. All right, let's see another example, and I'll try to make things a little bit more complicated now. So this was example 4. Now let me see example 5. Look at this monster. Okay, I would like you to think of it for a bit. You see, now you have the product of two functions. So you have secant square of x times tangent of x plus 3, everything to the 4th dx. So what do you think here? You see, it's you have secant square tangent of x plus 3, but maybe you can do something there. I don't know. So what do you think? What kind of substitution we should perform here? You see, let me give you a piece of advice. When you perform a substitution, make sure that the substitution will perform when you take the derivative of that, it's related to what it is inside the integral. So that's the trick you always have in mind when you perform a substitution. Let's see, Abdul says u equals tangent of x plus 3. Yes, that could be like a good idea. Why? And let's see why this could be like an option. So let's say u equals tangent of x plus 3. Well, if we take du is d tangent of x plus 3, but which is the derivative, the differential of tangent of x, which is what? Tangent of x will be what? It will be secant squared of x dx. Wow. Exactly. Look at this guy here, du here. Look at this guy here. Wow, look at this. We have dx here, we have secant squared. Wow, that's beautiful. Secant squared of x dx can be actually written pretty nicely in just du. Wow, beautiful. That's great. As you have see here, as you can see. And now this monster integral will be nothing else than just the integral of u to the power of 4th du. That's it. Right? And now you know to compute this guy will be 1/5 times u to the power 5 plus c, right? And now do not forget, I would like to say that again, you go back to the initial substitution, and this would be, and the initial substitution is right here, right? So when you go back to the initial substitution, right here, this will be 1/5 times tangent of x plus 3, everything to the power 5 plus c. And that's your answer. You see, it wasn't that hard, but it looked ugly at first. Let's see, any questions so far? There is a question here, let's see. Where did the 1/5 come from? When you compute the integral, u to the power alpha dx is, oh, okay, u to the power over alpha plus 1 plus c. Anyway, it's just no, that's good that you ask questions, because you might have some, you can blank out at some things, and you just, where is it, what does it come from? So don't be ashamed of asking questions, as long as it's all right. Let's see, any other questions? All right, let's move on then. Let's see another one. So example 6 now. Let me make this a bit even more nasty. Look at this guy here. So this was example, let's find this example 6. So in this example, we have to compute to find this indefinite integral. This time, you see, I'm not just asking for secant of x, right? Oh, I'm modifying a bit. So I'm asking for secant square of 3x times tangent of 3x plus 3, everything to the power 4th. So what should we do here? You see, I'm changing a bit. I have 3x there. So I'm just, u equals 3x. Okay. Let's see, u equals 3x. Let's try this. So du will be 3dx. But if I replace here, I'll have this integral of secant squared of u times tangent of u plus 3 to the power 4th, and dx will be 1/3 du. And now I go back to the initial integral. You see it here? Yeah, that could work, but then I have to do the work for the, and this is the previous integral. Okay, let me write it a bit, take the constant out. So this is 1/3 the integral of secant squared of u times tangent of u plus 3, everything to the power 4th, du. And this guy here, if you look at this guy here, this is nothing else than just the previous integral, right? So this is the previous integral, which you already computed. All right, but you have, and now you see, it's not a bad substitution, not at all. but I could claim that it is not the most efficient one, right? Because well, now I have to do the work for the previous integral. But yeah, you can, well, we have already done the work for previous integral and so on. But imagine in an exam, you have to do all this, all that, and you know, you wouldn't like that. Anyway, but what would be a much more efficient substitution here? Exactly. So maybe we. So maybe we should try something like u equals tangent of 3x plus 3. Great. Well, guess what? Here, du, well, if you take the derivative, we know that, and we apply the chain rule, right? This will be secant square of 3x times 3x, 3x prime, which is 3, dx, right? So we can write du in terms of dx, so we will have that this is nothing else than just this guy here. So 1/3 du is secant square of 3x dx. So this guy will give us this here. So the integral of secant square of 3x times tangent of 3x plus 3 to the power 4th dx will be, well, guess what? Nothing else than just u to the 4th times, right? Times du, right? Keep in mind that 1/3 du is secant square of 3x dx is 1/3 du. So, and now we're going to take the constant out, and now we can compute the integral. So let me just write one more step here. So this would be 1/3 times the integral of u to the 4th du. So this guy will give us exactly 1/3 times 1/5 plus u to the 5th plus c. And now I'll go back to the initial substitution, and then this will be 1/15 times tangent of 3x plus 3, everything to the power 5 plus c. So that's the final result. Make sure, and once again, I say, do not forget to go back to the initial substitution. This is very, very, very important for you. Don't forget to do that. You start, if they ask you to put the result in terms of x, and you make some kind of substitution, make sure at the end you go back to x. Well, that doesn't sound right. We go back to x, but anyway. All right, so let's see another example now. Well, like I said, we're gonna do a bunch of them. Look at this baby here. This guy looks innocent, but so we would like to find the integral of x over 1 plus x squared dx. So let's see. You see, you have a rational function here, so. But let's see, Abdul says u equals 1 plus x squared. Let's see. U equals 1 plus x squared. So let's see. What can we do? Du is what? Is d 1 plus x squared. And this guy will be 2x dx. All right, let's see. Oh, look at this. Look at this guy here. X dx. We can write this, right? Look at it here. It's 1/2 du. Phew, great. That's beautiful. That's exactly what I want. So again, as you can see, I have this. Once again, I have 1/2 du is x dx. So now I can write my integrals pretty simple as the integral of 1 over u times 1/2 du. 1/2 will take it out. And pay attention here, maybe I should mention this in more detail. So this would be 1/2 times the integral of 1 over u du. Well, this guy here, let me remind you, this guy is ln of the absolute value of u plus c. But now we're not done. Pay attention. I repeat this over and over. We have to go back to x. So u was, keep in mind that u, this guy here, u was 1 plus x squared. So when I go back to x, the final result will be this guy here. So it's 1/2 times the ln of 1 plus x squared plus c. All right, great. Now let's see another example. So this was example 7. But in fact, before I even go, let me remember something for you. Because I would like to do even more tricky examples. But before that, let me remind you some anti-differentiation rules. Remember when we computed the derivatives of the inverse trigonometric functions, such as arcsine, arctangent, or arcsecant, we got these functions like inside the integral, right? 1 over the square root of 1 minus u squared, or that's for arcsine prime. And then the derivative of the arctangent was 1 plus u squared and so on. Well, guess what? If we reverse now, if we take the antiderivatives of those functions, then we'll recover the inverse trigonometric functions. For example, in the case of the function of 1 over square root of 1 minus u squared du, if we take the integral of that, that would be arcsine of u plus c. And the integral of 1 over 1 plus u squared will be arctangent of u plus c. And then the integral of 1 over the absolute value of u times the square root of u squared minus 1 du will be arcsecant of u. So these are the rules. So make sure you keep this in mind. This is how we compute the antiderivatives for these, right? So keep that in mind. All right, great. And now let's see more examples. So that was example number 7. Now let's see example number 8. And let's think about it. So in this example, we would like to find the integral of e to the power x over 1 plus e to the power 2x dx. So what do you think about this one? Isn't it similar to the other one, like with x over 1 plus x squared? Well, first, let's see what kind of substitution we need. But first, let's rewrite this integral. Do you see something, some algebraic thing, some algebraic operation there? Well, yeah, all right, but before we go into that, look, this integral can be expressed, what e to the power 2x is e to the x squared. And now we can safely perform this substitution, e to the x equals u, then d e to the x is du, which will be equivalent with e to the x dx is du. Great. So we have this guy here. Wow, look at it. It's e to the x dx, that will be du. Wow, great. And guess what? Once we perform this, we'll end up with the integral of du over 1 plus u squared. And like somebody mentioned here, well, like Josh says, yes, exactly. This is nothing else than arctangent of u, tangent inverse of u plus c. But now we go back to the initial substitution, and this will be arctangent of e to the power x. So this is nothing else than arctan of e to the power x plus c. Right? You see? All right. Is everything clear about this example? So it's pretty much the same thing once you observe this this algebraic operation that, well, pretty obvious. You can write e to the power 2x as e to the x, everything squared. All right, beautiful. So now let's see another example. Let me complicate things a bit. So example number 9, look at this. Well, example 9. So what would you do here? You see, you have e to the power square root of x. So what should we do? U equals square root of x. All right, let's do that. Square root of t, sorry. So u is equal to square root of t. So du will be d square root of t, which will be 1 over 2 square root of t dt. Great. Which we have here, if you see. We have here, right? Look at this here. So our integral, let's see what would become. So this integral will become e to the power u over dt, it will be 2 du. So let's put it here. Over e to the power u plus 1. All right, great. You see, we didn't get rid of e to the power. We still have the exponential there. What next then? You see, maybe it's not the most efficient substitution you could perform here, because now we have to be careful here. So there are a bunch of operations that we need to perform at this point. Because we don't know how to take care of this guy. See, what about this guy? What are we going to do with this? Maybe we can add 1, subtract 1. We can play with the algebra. Yes, we can do that. I agree, but it's a lot of work. That is the problem, and I don't want to do a lot of work here. I want to do something that goes just like that and makes my life easier, way easier. I didn't say it's a bad substitution, it's not, but I don't think it's the most efficient one. So I could leave this to you as a homework to deal with this integral. You can do it. Let's see, some other suggestion. U equals e to the power square root of 2. Maybe you try to, yeah, square root of t, yeah, that's what you, yes, you can do that. Let's do that as well. So e to the power square root of t equals u, right? And let's see, d from here, du will be de to the power square root of t. But this guy will be e to the power square root of t times square root of t prime, which is 1 over 2 square root of t dt. Wow, let's see. And our integral, all right, so e to the power t over, yeah, it will be du. So our integral will become what? Let me write it here. This would be the integral of u over e to the power u plus 1 times 2, right? Du will be 2 e to the power, actually no, wait, what am I saying here? It's already, sorry about that. So it's already 1 here. And here, du, so pay attention, let's look who du is. So this guy here, du, is this guy here. So 2 times du is e to the square root of t over square root of t. So this will be 2 times du, right? Well, again, we still have e to the power u there. You then get rid of it. You have to deal with it as well. Well, again, you can deal with this integral easily. It's like ln of, well, if you look at it, but again, you have to do a little bit of work. Still, you can deal with this. But I want something that goes even quicker. And that's good that you tried all this substitution. That's the way it should be. Because you try all these substitutions when you deal with this integral, you will see which one is makes your life the easier, or you like to see something that will make your life as easy as possible. Well, look at this. Let's perform this substitution. Let me just add this constant because it bothers me. You see, this plus 1 here, this integral here, this bothers me because if I didn't have it, then life would be much easier. So why not include that constant as well in the substitution? So let's do that. Exactly. So let's do that. And again, when I take the derivative, when I take the differential, there is no problem because the constant will just vanish. So we will have the same thing. So 2 times du is e to the power t, or e to the power square root of t over square root of t dt. So this would be the integral of e to the power square root of t over square root of t. So that integral over there, that mass, will be nothing else than just this guy here. And we're going to take out the constant. So this would be 2 times the integral of 1 over u du. And of course, you can compute this. This is 2 times ln of absolute value of u plus c. And this is 2 times ln of, now we go back to the substitution. Pay attention, do not forget to do that. So in this case, the variable was t, and we can write this integral as this guy here. Right? All right, great. Let's move on. We have plenty of things to do. But first, are there any questions regarding this example? I think we explored this one in 3 ways, so I hope it makes more sense. Let's see, any questions? Okay, let's move on. But before that, let's see, let me give you some other a plethora of anti-differentiation rules. As you can see here, the integral of sine of u, cosine, secant square, cosecant square, secant times tangent, cosecant times cotangent, and so on. All of them are right here. So we have done this for the derivatives, right? But also we have done this for, we would like to see what happens for the antiderivative, right? Well, we can actually compute the antiderivatives of sine, of cosine, of secant square, cosecant square, and so on. All right, so these are the rules. So I would like to use that. And let's see some other examples. I want you to have another good look at these. All right, now let's see some other examples, and I would like to dwell more on trigonometric functions. And the first one that I have in mind is this one. I think this is example number 10 at this point. So we would like to find the integral of tangent of x dx. So in the indefinite integral. So what should we do here? Well, I already said what tangent, well, I did not, but maybe we can somehow make this look like something that's right here. So what do you think? What kind of substitution should we perform? Well, you see, now you look at it like, whoa, what the hell is the integral of tangent of x? What should I do here? Because you don't see any obvious substitution. Well, if you don't see anything that's super obvious to you, maybe you should do what? Maybe you should just take the tangent of x equals u. Why not? Right? Maybe you should perform this substitution. So let's do it. Tan of x equals u. D tan of x is du. Right? So the derivative of the tangent is what? Is what? Is secant squared. Oh, secant squared of x dx is du. Jesus. And I don't have anything with secant squared there, right? You see, do you see any secants here around here? No, not quite. Oof. So what should we do? Maybe this is not the right one. Not a good one. Definitely not a good one. So maybe we should do something here. All right. Let's see. Do you remember what the function tangent is? Is what? Is the integral of sine of x over cosine of x, right? Dx. So I have cosine of 1 over cosine of x dx. All right, maybe I could perform another substitution, and maybe a good one will be the following. So again, we can write this in this way. Look at this here. So maybe I could perform this u sub u equals cosine of x. Well, in this case, we will have that du is negative sine of x dx. Great, that's actually beautiful because I can express all the term, I can express all these guys here inside this integral, right? All of them. And I can write them the following way. Well, u 1 over cosine of x will be 1 over u, but du negative sine of x dx, or if you want sine of x dx, will be negative du. So we'll end up with this guy here. And you know how to compute the integral of this guy? We have already seen that is nothing else than just the ln of u, right? Let me remind you that is ln of absolute value of u plus c, right? So we're going to use that. And now I'm going to go back to the initial substitution, and guess what? This will be nothing else than just negative ln of absolute value of cosine of x plus c. Or if you want in an alternative form, you can say that this is the integral of the tangent is ln of the absolute value of secant plus c. You can also write it in this way as well. All right, let's see another one. So this was example number 10. Let's see 11. What about this one? Look at this. Example 11. I would like to find the integral of the cotangent of x dx. Well, I hope you don't mind, but I'm going to keep you a bit over time today. Maybe, I don't know, 5-10 minutes at most. Yes, there is a yes. So there was a question here. Is there a link with, actually it's in my notes with all these trigonometric derivatives and stuff. If you look at my lecture notes, you'll find them all there. I will send you an email where I will indicate exactly where to find those, the antiderivatives of all trigonometric functions, and not just that, all of them, all elementary functions. So they're in my lecture notes in chapter 5. You'll see there's a, well, I'll send you an email. All right, let's see this one. So the integral of cotangent of x dx. What would you do here? Well, guess what? You'll perform the substitution u equals sine of x. So because in the cotangent is cosine over sine, so this time you'll do the u sub will be u equals sine of x, and then du will be cosine of x dx. So the integral of cotangent of x is cosine of x over sine of x dx, right? Which is, well, like I said, is now with using the substitution, it will be du over u, the integral of that. Well, again, this is pretty easy. Is the by the same considerations as in the previous example, this will be ln of the absolute value of u plus c, and now we go back to the substitution. This will be ln of the absolute value of x plus c, of sine of x plus c, and guess what? We can write this in the following alternative form, which is this guy here. All right. Let's see another one. In fact, you know what? So that I wouldn't, I'm going to give you the other one. I'm going to leave this to you as a homework. So to find so this is example number 12. This will be for you as a homework, so that I won't waste my time in this lecture. Again, you have to perform you have to write the secant in some way. It's a bit tricky, but anyway, I'll leave it to you as a homework. And now, oops, sorry about that. And now, let me move to this one here. fact, let me just describe it. To find this integral, this time we deal with the definite integral. Example 13. So we like to find the definite integral of from 0 to 2, pay attention now, of x squared over, or if you want x squared times 1 over square root of x cubed plus 1 dx. Well, here you'd perform this substitution, u equals x cubed plus 1, right? So du here will be 3x squared dx, which you'll find here. We'll write it in this way. And now let's plug it in, let's change the variable. And now I will forget for the moment that I'm dealing with a definite integral. So forget about the bounds at this point. So you're just gonna look at the indefinite integral. So our indefinite integral without the bounds will transform into the new variable, which is u. So this will be the integral of 1 over square root of u times 1/3 du, right? We can actually compute this. So this we can write this 1/3 times the integral of u to the power negative 1/2 du. We can compute this right? And we end up with this guy here. Look at it. Well, now we go back to the initial variable, which is this. And this would be 2/3 times square root of x cubed plus 1 plus c. Great, and now we can take the bounds into consideration. Look, now I can deal with the definite integral, and I can apply the fundamental theorem of calculus, right? And once I do this, well, I take the antiderivative, which is 2/3 times the square root of x cubed plus 1 from 0 to 2, and I just plug it in using fundamental theorem of calculus. This will be just like, anyway, I just plug it in for 2, x for 2 and x for x, and I subtract the 2, and it will end up with 4/3. All right, so that's an example. And well, like I said, I'm gonna go a bit over time. I apologize for that, because I'd like to finish what I had to discuss today. Now let's see another example, but before that, let me just mention the alternative way of the change of variable, or the u sub, and it's this guy here. Well, as an alternative, we would like to determine the limits of integration for the variable u, right? Rather than to convert the antiderivative back to the variable x, and then we evaluate at the original limits, right? So we can do that, because here, if I go back here, you see, I changed the variable, but I evaluated the indefinite integrals. The indefinite integral, and then I went back to my initial integral, and then I put in the initial bounds. But I don't need to do this. Once I change the variable, I also change the bound. So either way, it doesn't matter how you do it. You can just, it will give you the same result. All right, let's see another example. So this was example 13, now example 14. Look at this. You see, it's the same problem, but this time I would like to do it in what I just described. This is example 13. All right. Again, I would like to compute the integral from 0 to 2 of x squared times 1 over the square root of x cubed plus 1. Well, in the same fashion, I would like to use this alternative method. Again, we perform the same substitution, but now I'm not evaluating the indefinite integral. What I am doing right now is I'm changing also, once I'm changing the variable, I'm changing also the bounds of the integral. So let me just mention here something. How do I change the bounds? That is the question. So the question is, how do we change the bounds of the integral? Well, when u equals, let's see, when u equals 0, sorry, when x equals 0, I'm sorry about that. When x equals 0, right, u will be what? Will be 1, right? Because, okay, let me say it's u 0/3 plus 1, which is 1. When x is 2, then u will be 2/3, 2 to the power of 3 plus 1, which is 9. And there you go. Look here. You see the bounds? 1 and 9 here. Great. And now I changed everything. So everything, also the bounds, also the variable, right? And I don't need to go back because the definite integral, we said this will be a number. It's not going to be like the indefinite integral, which will be a function. This will be a number. And now I can easily compute this. So this guy here, so I'll take 1/3 out. So this will be 1/3 times the integral from 1 to 9 of 1 over square root of u du. And again, I can write this as 1 over square root of u. I can write it as u to the power negative 1/2. And I can compute here, right? I can find the antiderivative of this. Again, why? Because the integral of u to the power alpha du from a to b is u to the power alpha plus 1 over alpha plus 1 from a to b. And now we're just going to replace. So this would be b to the power alpha plus 1 over alpha plus 1 minus a to the power alpha plus 1 over alpha plus 1. So, and now you're just going to take from 1 to 9 because our bounds are 1 and 9, and then you just plug it in. Basically, this will be just algebra, right? All right. There is another example, and I think I will leave this to you as a homework because I don't want to go too much over time. So this example here. So this is example number 15. So leave it to you as a homework to figure it out, which says the following. And it's pretty easy actually, but anyway, I'll leave it to you as a homework. If the integral from 2 to 3 of f of, and pay attention, the variable inside is 5x minus 2. So if f of 5x minus 2 dx is 4, then what is the integral from 8 to 13 of f of u du? Anyway, now let me veer towards 2 more examples, and I think I'm going to stop after this. Is example 16 and 17. So look here. I would like to compute the integral from 0 to 1 of x times x squared plus 1, everything cubed. Again, a good thing for us is to perform this substitution, right? Because if you look at u equals x squared plus 1, then du will be 2x dx, right? Or you can write it as 1/2 du is nothing else than just the x dx. And I would like you to pay attention because this is important. Before substitution, we need to determine the new limits of integration. So the lower limit, or the lower bound, will be when x equals 0, right? Because we have to find the integral from 0 to 1. So here, pay attention, this is when x is 0 and x is 1. So when x is 0, u will be what? Is 0 squared plus 1, which is 1. And the upper limit, when x equals 1, u will be 1 squared plus 1, which is 2. So now we can turn everything into variable with variable u, and let's do that. So it will turn out that our integral will be nothing else than just, well, if you look, the integral from 1 to 2 of u cubed du over 2. We're going to take 1/2 out, and we're going to end up with this integral. But we know this integral is nothing else than just u to the power 4th over 4 from 1 to 2. And we can actually compute this by using fundamental theorem of calculus. Well, as you can see, it's right here. So this is from 1 to 2. And just basic algebra, we'll end up with 15 over 8. I'm going to leave this to you as an exercise to figure out the algebra. I don't want to lose time with that. All right, and one more example. So this was example 17. I want you to have your attention for one more example, and I think we'll stop here. What about this guy here? You see, what about the integral of from 1 to 5 of x over the square root of 2x minus 1 dx? What about this one? What kind of substitution would you perform here? What do you think? So maybe I should perform directly the square root of that, right? Maybe I should do u equals the square root of 2x minus 1. So du will be what? Will be 1 over 2 times the square root of 2x minus 1 times 2x minus 1 prime, which is 2. Great. You see, I have it here. Look at this, times dx, I'm sorry. Look at this guy here, look at it. I have it here. Great. So at this point on, I can say that dx is 2 to the power 2x minus 1 to the power 1/2, or if you want, dx will be u du. Because you see how nice I can write this. Because here, this guy inside here is u, is our well, all of it. Sorry, not just the guy inside. All of it is u. Right, as you see here. All right, great. Now we can keep in mind that we would like to change the bounds of the integral, right? So the lower bound or the lower limit is when x equals 1, u will be 1, and the upper limit is when x equals 5, u will be 3, and then we keep going. So this, our integral will become this new integral here, this mess here. But it doesn't look quite like a mess because these two will just go away and we'll end up with this guy here. And anyway, I think at this point you can do this by your own. You can find the antiderivative of this. You can use the sum rule for the integrals, right? This will be 1/2. Let me just write it here, and then you will times the integral from 1 to 3 of u squared du plus the integral from 1 to 3 of 1 du. That's it. And then you'll go here. And after that, there is just algebra. We'll end up with this guy. Anyway, I'll leave this to you as an exercise to figure out all the algebra, since I don't want to deal with that. All right, guys, I apologize that I went over time, but I wanted to, I went a bit faster at the end, but I think the video was recorded and you can go back to, once I post the video on my channel, you can go back and, pause the video when you have some kind of, if I went too fast or anything like that. All right, I think this is a very important lecture. This will be very relevant for your Gateway 2 exam, which will be this week. but also for your final exam as well. Well, at this point, we're actually getting closer to the final lectures. Well, basically, we're gonna wrap up the entire course very soon. So we have left, I think, 2 more lectures. The next time I will do this, next time will be a very short lecture. We'll talk about the mean value theorem, and then next Monday, which I haven't decided if it will be a live lecture or not, but in any case, it will be recorded. We'll talk about numerical integration formulas. We'll see methods of how to approximate integrals if we cannot compute them. All right, guys, I think I'll stop here. I'll have office hours like now if you have any questions. I'll see you. Bye-bye.